Welcome to Maths with EJD. In this video, we switch from convex optimization to non-convex optimization. So straight to it, we have the overview. So non-convex optimization, of course, since we've already understood the idea of convex optimization, we can maybe take a cue from that to understand non-convex optimization, which refers to problems where the objective function or constraints are not convex, meaning they may have multiple local minima or maxima. Of course, one beauty of a convex function is that you can have one local minimum or one local maximum, because most of the time they're either facing up or down, and then you have a maximum or minimum point clearly, even from a graph. So convex functions may have multiple local minima or maxima, and the global optimum and the global optimum may not be may not be easily identifiable, because the feasible region, of course, is boundless, so to speak. All right. Now, these problems are more complex than convex ones because gradient-based methods might get stuck, might get stuck in a local extremum. That means you can get a local minimum that is not really the global one, right? They might get stuck in a local extremum and fail to find the global optimum. Okay. Um, non-convex optimization is relevant in many areas, such as machine learning, neural network training, and signal processing, where the objective functions often have non-convex landscapes. Okay. Now, let's talk about key concepts in non-convex optimization. So first of all, let's look at convex versus non-convex functions. So in the previous videos, we had looked at convex functions and their property. So first of all, a function f of x is convex if for any 2 points, x1 and x2, the line segment joining f of x1 and f of x2 lies above or on the graph of the function. Okay. Formally, we have f of lambda x1 plus 1 minus lambda x2 to be less than or equal to lambda f of x1 plus 1 minus lambda f of x2 for lambda in the closed interval 0 to 1. Okay, so that is the condition for convex functions. So then let's talk about the optimization problem for convex functions. So two, convex optimization problem, that is optimization problem. Okay, so minimize f of x. Here, this is the one dimensional because we're just talking about only x. So in the next video, I'll be talking about non-convex optimization in 2 dimensions where we talk about x and y. So minimize f of x subject to gi of x less than or equal to 0, I equals 1 to up to m, and then you have hj of x. These are constraints. The first one is an inequality constraint. This other one is an equality constraint. J start from 1 to 2 all the way down to p. So these are constraints, inequality and then equality constraints. Now, the next thing we like to look at will be the challenges in this situation. Talking about number 3 under this. Let's look at the challenges of non-convex optimization. So the first thing is the idea of local minima. So unlike convex functions, which guarantee a global minimum, non-convex functions may have a non-convex functions may have many local minima, making it difficult to find the global minimum. Okay, then we also have the idea of gradient descent. We have gradient descent limitations. This is one of the gradient-based methods. Gradient descent limitations. So common optimization methods like gradient descent can easily get trapped in local minima or saddle points. Because they only use local information So it's more like there's a vast field of possibilities, and then you settle on only one, thinking that's the best you can have. That's the idea here. So let's look at some methods for solving. So we've talked about the challenges, right? Um, so that would be like number three. So let's call this number four then. So let's call this number four. What are the methods? Methods to solve non-convex non-convex optimization. Okay, so you can talk about gradient descent with restart. Since the normal gradient descent will not do the job, gradient descent with restart. So to escape local minima, the algorithm is restarted from different initial points multiple times. Okay. So then there's another method you can use. We have seen all these methods interestingly. So we can use simulated annealing, which takes idea from metallurgy and cooling. So we can use simulated annealing because here it's easy to escape local minima. So this probabilistic technique allows the algorithm to jump out of local minima by accepting worse solutions based on a decreasing temperature parameter. Then we can also use genetic algorithm, which is a derivative-free method. Genetic algorithm, genetic algorithm. Simulated annealing is also a derivative-free method. So get genetic algorithms, this use principle of evolution to explore the solution space by combining the best solutions over multiple generations. And then we can use random search to also solve non-convex problems. Random search. So this technique samples random points and explores a wide solution space. Since in the first place, by its very definition, non-convex optimization has a very wide array of space. So it's difficult to get a specific local minimum or local maximum. So since we are talking about one dimension, let's consider that in this situation. Okay, let me go this and then this. So example, consider consider the non-convex function f of x equals x raised to the power 4 minus 3x squared plus 2. Okay, so if we want to minimize it, right? Right. So the first thing you want to do is step one, right? Step one, plot the function. Plot the function. So you need to plot the function to see what it looks like. Thankfully, of course, it's easy to plot this particular function, but I'll just, as usual, I'm going to use Desmos for the plotting. So we go for the plotting of the function. So we are talking about x raised to power 4. Then you have minus 3x raised to power 3, then plus 2. So as you can see already, this is x raised to power 4 minus 3x raised to power 3 plus 2. So, so you see what the function looks like. X raised to power 4 minus 3x cubed plus 2. This is what this looks like. And here, um, so this is what it basically looks like in short. Okay. So imagine that I have if I have a line, we can have a line coming from here. Let me even see what line I can use here. This is we can have a line that cuts across. Let me think of a very good line I can do here. Let's say x plus y equals minus 3. Okay. Okay, let me move it up a bit. X plus y equals, say, 4. Okay, that's looking like convex. Let me shift it to 2. X plus y equals 2. Yes, exactly. This is a very good one. So you can see the line is cutting across the function in different places. So if you take this point, if we take this point now where we have minus 0.5 against 2.5, and we take this, so you see that line is cutting across the function in different parts. So it's cutting across the function in like four different parts. So that is a very good example of convex function. So you can get a minimum point. For instance, if you get this value as minimum point, there's still a global minimum down here. So this is a very good example of a convex function. So the first thing you want to do is to plot the point, plot the function. And once the plotting is done, then of course, what does this plotting involve, right? Um, so first, plot f of x to observe its shape. So we have seen the shape there to observe its shape. So it is by no means convex. So observe its shape. Okay. So we expect multiple local minima and maxima. As you can already see from that, local uh multiple local minima and maxima. Okay, I mean, so I have shown you what the plot looks like from the other page. So let's go for step two. Step two. In step two, we find the critical points. Find critical points. Okay, what that means is you take the first derivative, take the first derivative of f of x. So of course you already know f of x is x raised to the power 4 minus 3x cubed plus 2. So first derivative f prime of x will just be 4x raised to the power 3 minus 9x squared. 2 is constant, so that just goes to 0. So we can equate this to 0. 4x cubed minus 9x squared is equal to 0. So x squared is common into x squared is common, right? So into 4x minus 9 equals 0. So that simply means that we end up having x squared equals 0 or 4x minus 9 equals 0. So that means x is equal to 0 or x is equal to 9 over 4 or 1.25 or so or something like that. So these are the two values of x. Okay. So next thing is step 3. Step 3 now, where we analyze the critical points. Analyze critical points. Okay, so to determine whether, so we have got the critical points as 0 and 9 over 4. So to determine whether these points are minima or maxima, we take the second derivative of f of x. Okay, so now we have f prime of x, the last f prime of x we have. So of course, maybe I can even start again. F prime of x. Let me start from f of x itself. Again, f of x equals 4x cubed minus 9x squared. So f prime of x is equal to no, this is x raised to power 4, right? Okay. So this is x raised to power 4, x raised to power 4 minus 3x cubed plus 2. So f prime of x is 4x cubed minus 9x squared. So second derivative f prime prime of x will be 12x squared minus 18x. So that is the second derivative. So here now, we can evaluate. So we have two critical points, x equals 0 and x equals 9 over 4. So we can say for x equals 0, so f prime prime of 0 will just be 12 into 0 squared minus 18 into 0. And all of that is 0. I want to get 0 like this. It is inconclusive. So this is inconclusive. We don't really know if it is minimum or maximum point. So this is inconclusive. So we have to check higher derivatives to be sure of this. Check higher derivatives or other methods. for this particular zero, okay? So that goes. Then we can also check the other one. So for x equals 9 over 4, so second derivative is f prime of x, f prime prime. We have f prime prime of x equals 12x squared minus 18x. So that means that f prime prime of 9 over 4 is equal to 12 into 9 over 4 all squared minus 18 into 9 all over 4. So that means we have 12 into 81 over 16 minus 18 into 9 over 4. Okay, so that is so if you work that out, 81 times 12, that is 216, and this is 81, that is 972. So this is 972 minus 18 times 9. 18 times 9 is 9 times 9 times 2. That's 81 times 2. Okay, this is all over 16. So this is 9 times 9, 81 times 2. 81 times 2, that is 162 all over 4 down there. So this can go. And then we are back here. So this is LCM is 16. So we have 972 minus 4 times 4 is 16, 4. So 4 times 1, 62. That 4 times 2 is 16. We have 1. 4 times 6 is 24. That's 25. Carry 1. 4 times 1, 5. So that's like 556. So we have 972 over 556. So 972 minus 556, rather, minus 556. So this is 6. And this remains 6. 6 minus 5 is 1. And this is 4. So that's like 416 all over 16. Okay, 416 over 16. 416 over 16. We can quickly use decimals for that also. 416 over 16. So I can just do this. 416 divided by 16. 416 divided by 16. In the first place, right? Let me even do the original thing to be very sure that that is correct. 416 over 16 is 26. So what we did was 12 multiplied by 81 divided by 16 minus 18 minus 18 multiplied by 9 over 4. That is 20.25. Why is this different? 81 over 16, that's 12 times 81 over 16 minus 18 all over 9 over 4. That is 20.25. 20.25. Okay, the other one I did was 972. So we have 972 minus 556 divided by 16. Okay, I must have made a mistake up there. Okay, let's leave this. Let me cut this out. I want to be sure. So this is 60.75. Then this other one is 40.5. 60.75 and 40.5. So there must be a mistake somewhere. So so it's 1 over 16, right? So this is 4. Okay, I guess let me just write down the answer and just move because of time. So you want to confirm all of this. So from what we have got, right, this is 60.75 minus 40.5. So that is 12 times 81 all over 16. And that is 20.25 or so. Is that the idea? Let me check again. 12, yeah, 60.75 minus 40.5. 60.75, 60.75 minus 40.5. That is 20.25. Okay. 20.25. Okay, that works. So basically, because this is this positive value now, okay. So that means we have so now that means f prime prime of 9 over 4 is equal to this now. So we can say this is positive, and because it is positive, that means the local minimum. If it was negative, that would be a local maximum. So it's a local minimum. So we take care of that. So then we can move to step 4. In step 4 now, we have to talk about the conclusion. So the function, since you are looking for minimum, right? The function has a local minimum. The function has a local minimum at x equals 9 over 4. We can then evaluate the function at that point. Okay, we can then evaluate the function at that point. Okay, yeah, since we know 9 over 4 is a local minimum, and that is about what we are looking for, so we can evaluate the function. So the function is, we have 9 over 4 raised to power 4 minus 3 into 9 divided by 4 raised to power 3 plus 2. So that's what we have. We can even have it in fraction. Yeah, that is minus 1675 over 256. Minus 1675 over 256. I like fraction like that. Minus 1675 over 256. And the function, original function, right? F of 9 over 4 is minus 1675 divided by 256. So that's the minimum point of that particular function. Okay, so the function has a local minimum at x equals 9 over 4 and f of 9 over 4, right? The function itself evaluated at that point. The objective function is this, you know, of course, and you can confirm this by plotting the function to see that there are other local minimum and maximum in the solution space, just like we saw before. So non-convex optimization problems often require starting from different points to ensure the global minimum is found. Okay, so that happens. All right, before we round this off, let's see the Python code for this to drive home the point again. Okay, so non-convex optimization in 1D. To look at all of this, okay, I think I had run it before to show the answer. Let me just clear all the outputs and try to explain a little bit before going. All right, so we have the function, we have the gradient of the function 4x cubed minus 9x squared. Then we have the gradient descent in setup. The learning rate is 0.1. That's like the step size, so to speak. The maximum iteration is 1000. The tolerance is 10 raised to minus 6 and all that. The initial value of x is 2. That's just picked. Of course, we know 9 over 4 is the answer, which is like 2.45 or something. That's 214. That's 2.25, yeah? So, and if you go all that and we run this, okay, so it just goes all the round, and then we have several iterations. So after 1000 iterations, the value of x is 2.1475. Interestingly, I think, okay, 9 over 4 is what we got, right? Print 9 over 4. Okay, this is not working. Print, small letter, print 9 divided by 4. So 9 divided by 4 is the answer that we got there. So that's 2.25. So from the iterations we got, we got that to be 1000. After 1000 iterations, we got 2.1475. And the function is itself evaluated at minus 6.4295. So and remember what we got over there is like this. We have minus 1675 divided by 256. That was what we got. And that is minus 6.54. Here we have minus 6.4429. That's pretty close. And this is the graph. So you can see that the value, so gradient descent is used here. So you can see the value is keeps descending until we arrive at 2.1475 as far as the code is concerned. Okay, but thankfully, I mean, we're already able to get we're already able to get the answer, even without the code already. So, but there, some things can get really complicated and you're unable to use the code directly. So, to conclude this, non-convex optimization involves challenges such like multiple minima, saddle points. So saddle points are points that are never stable or unstable, right? Like they're just in between. So methods as gradient descent, such as gradient descent with start, simulated annealing, and genetic algorithms are typically employed to uh, navigate this kind of problems, right? To navigate the complex solution space. Analyzing the critical points and using numerical or heuristic methods can help in finding the global minimum or a satisfactory solution to these types of problems. So let's look at practice questions. Let's take one or two to round this off. So for practice, okay. Um, and I'm trying to get a nice one. Okay, solve the minimization problem numerically for f of x comma y equals sine xy plus x squared minus y squared. Okay, so you want to solve that. Then what else? I'm trying to look for another one. Okay, that is one. That is one. Two. This is one now. So for two, find all local minima of f of xy equals cos x plus cos y plus xy. Okay. Yeah, that will okay. I think I found one that I find it difficult to resist. Something in machine learning. In training, in training, in training a neural network, in training a neural network, the loss function, the loss function is given by L, the loss function is given by L of W1 comma W2, which is equal to e raised by minus W1 squared minus W2 squared plus W1 minus 1 squared plus W2 plus 2 squared. Okay. That's what we have. So explain why simple gradient descent, while simple gradient descent may struggle with convergence, may struggle with convergence. So that is non-convex optimization in machine learning right there. Okay, so that's what we have for this video. In the next video, I'll be talking about two dimensions. I'll be talking about X and Y. So let me know the solution to your problem, to these practice questions in the comment section, either on YouTube or on Facebook. Then you can also find the code on Facebook, not on YouTube, and you can copy it out and try it out in Jupyter Notebook or any other IDE you get to use. So I mean, you can see the application in machine learning, which is really relevant these days. Okay, so try to look at this and let the point sink in. All right, so if you have subscribed to this channel, thank you so much. If you have not, please go ahead and do that and hit the notification bell so you can always get alerted each time a new video is released. Let me also know in the comments how helpful you find these videos. If you also have a topic you'd like me to teach or a problem you'd like me to solve, please indicate. I may be able to find time to do that. And then lastly, like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Watch out for the next video on non-convex optimization in 2 dimensions. Bye.